We are on question 4, and we have the given line segment VZ congruent to line segment VY, and line segment WY congruent to line segment XZ, and we're trying to prove the line segment VW congruent line segment VX. The if is the given, and the then is the proof. So yeah, you want to take the if as given, then as proof. Of course, we start with our t-chart and we list our givens here. Our reason is going to be given. Right? And using our algorithm over here, what is our next step? Well, we wrote down our statements and reasons. We wrote down row 1, and so next is there any congruent statements? And if there are, then convert them to equations using definition of congruent segments. So that's what I'm going to do, because I have these congruent statements. So I'm going to say to VZ, measure VZ equal to measure VY, and measure WY is equal to measure XZ, and then that is def congruence. What is our next step here is if there's any midpoints given, then create an equation using definition of midpoint. If there were midpoints given, then right here on the if, it would say, point X is a midpoint of VZ. It would say midpoint here in the given, but it does not. So there are no midpoints given. What's our next step is we look at the figure, and if we're given 3 points on a line, we create an equation using segment adpos, right? Which says first part of the segment plus second part of the segment equals the whole segment. So if we look at this figure, you might be looking at it and be like, hey, what is that again? It's a triangle. It might throw you off. However, we do have 3 points on a line, namely Y, W, and V. Okay? So I cover up these 2 points, and my points are Y, W, and V. I can create an equation using those 3 points, using seg adpos, and I will, namely VW plus WY is equal to VY. And not only that, but now I can cover up those 2 points, and I have another 3 points. I got V, X, and Z, so I can make another equation using seg adpos. So it's going to be Vx plus Xz is equal to Vz, and that is seg adpos. Alright, so going back to our algorithm, what do we do after we use seg adpos? Last step is to use substitution to try to get to the proof statement. So we're trying to prove VW is equal to Vx. So how can we do that? Well, I'm looking at this and I'm thinking, where can I substitute what, right? And so here we have an equation, and an equation means anywhere I see the left side, I could put the right side. Anywhere I see the right side, I could put the left side. And so what I'm going to do is I'm going to take this left side and I'm going to put it in the place of Vy right here. And I'm able to do that because this expression is equal to Vy. Okay. Next, I'm going to go ahead and take this expression here, and I'm going to substitute him for Vz right here. And I can do that because this equation says that this expression on the left side is equal to Vz. That means anywhere I see Vz, I could put this expression. So that's what I'm going to do. I'm going to put this there, and I'm going to put this expression there. Okay, that's how that substitution is going to work. So 4 is going to be Vx plus Xz is equal to Vw plus Wy. So 4 is going to be substitution. Okay, so now what do we do? Well, we want Vw to equal to Vx. So we want Vw equal to Vx. So we want the Xz and the Wy to go away. We can make them go away if they're the same value. If it was Wy and Wy on both sides of the equal sign, we could do subtraction and subtract Wy from both sides of the equal sign. These two expressions will go away, leaving Vx is equal to Vw. Right? So basically, we need to turn this into a Wy. And can we do that? Is there any? The only way that we could do that is if there is a equation that we have stated that says Xz is equal to Wy. And do we have that? Well, do we have it here? No. Do we have it here? No. Do we have it here? No. Do we have it here? Yes, we do. Xz is equal to Wy. Okay. So what I'm going to do is I'm going to take this Wy and I'm going to put it in the place of Xz right there. So I'm taking him and I'm putting him right over there. Okay. Substitution. So it's going to be Vx plus Wy is equal to Vw plus Wy. Now we're looking better because we have the same expression on both sides of the equal sign, and we can get rid of them by using subtraction. So it's Vx plus Wy minus Wy is equal to Vw plus Wy minus Wy. My writing is a little messy here, but this is subtraction, right? And then we're going to go ahead and replace this Wy minus Wy with 0. We're going to replace this Wy with minus Wy with what it's equal to, namely 0. So we're going to be left with Vx is equal to Vw, and that is a substitution. We are substituting this expression for what it's equal to 0. We're substituting this expression for what it's equal to 0. So this guy here is a substitution. All right, so we're almost there, right? If you look at the proof statement, we're almost there, except it's the wrong way. We need Vw to be on the left side. So how do we do that? Well, now we're looking at our proof sheet, and which of these algebraic proofs lets us do that? Well, you're going to gravitate towards reflexive. I don't know why, but everybody gravitates towards reflexive. Reflexive states same equals same. A equals A, 5 equals 5, 7 equals 7. We're not using reflexive until further down, so forget about it. Right? What lets us flip the equation? Symmetric property lets us go from A equal B to B equal A. It lets us flip an equation, symmetric property. So we're going to say Vw is equal to Vx. Number 8 is symmetric property. Now what do? Well, up here on the proof, right, we don't want equals, we want congruent. Well, that's what the proof is trying to, that's what we're trying to prove, is the congruent statement. So we need to go ahead and turn this equation into a congruent statement. So it's Vw, line segment Vw, now the line above comes back, is equal to line segment Vx. And that, of course, is our definition of congruence, which lets us go from equal sign to congruent statement, or from congruent statement back to equal sign, right? We used it up here to go from congruence to equation. Now we're using it down here to go from equation back to congruence. Yeah, I think I might have said that wrong. Congruence to equation, and then equation to congruence, right? Definitions let you go both ways. It lets you go back and forth from equation to statement and statement back to equation. Anyhow, this is that problem.